Okay, welcome back from the break. What I'd like to do is to talk about the topic that you see on the screen here this afternoon, and that's several different subjects. The basic theme is to look at screening non-targeted compounds. In other words, those compounds that do not exist on typical food MRL lists. These are new food contaminants or new food ingredients. And so that's what we mean by non-targeted screening. And of course, the difference between screening and an analysis is that when you're screening, let me do it the other way. When you do an analysis and you generate an analytical report, what most laboratories find is in the analytical report, it says non-detect, 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 non-detect. In other words, your sample was clean. Well, that takes a lot of sample preparation, it takes a lot of analysis time, and it takes a lot of data processing time. So screening is a much more efficient way to go, and what I'm going to show you today is to screen through a sample there that you may look for target compounds and non-targeted compounds. And if you get a positive hit on any compound, you do not have to rerun the sample. You simply go back to the data file and you take that peak that is a positive and you simply then do confirmation and you do quantitation. So screening really means one pass through the analysis instead of multiple injections. And that's a big difference. Now, to do that and to accomplish that, I'm going to talk about what some people call high-resolution mass spectrometry. I prefer to call it high mass accuracy mass spectrometry because that's exactly what we're trying to get to, is very high mass accuracy. If you had the molecular weight of any compound to 6 decimal places, I can assure you that you know exactly what that compound is. If you know the molecular weight to 6 decimal places, there is no ambiguity about these compounds. So that's where we're trying to get to. Now, to illustrate this, there's several cases I'll show you very quickly. But melamine, for example, when it was discovered in cat food and dog food in the year 2007, melamine was an unknown. Nobody had ever had melamine on a list of target compounds. Then, when melamine reappeared in 2008 in powdered milk, in dairy products, in candy, and other products, again, nobody was looking for melamine as a targeted compound. In fact, today at lunch, we were talking about now melamine has even been found in fish because it's in fish food. And it's in fish food for a very good reason, and that is it slows the dissolution of fish food in a pond of water. In other words, the fish food lasts longer if the binder is melamine. Well, that's good. That's wonderful for the farmer. But for you and I, then we eat the fish, and we just ingested the melamine with the fish. Okay? So the melamine story is well known, and it's an example of a non-targeted compound. Now, this morning you heard John Gilbert talk about Sudan dyes, and of course Sudan dyes have been around quite a while, but as he pointed out, in fact, some of the Sudan dyes may be carcinogenic. They are not approved for the use in foods. They're usually used for things like making products a better color, giving them a richer color. And I think the example he used was chili powder and curries, also with eggs and egg yolks. You know, you can make the egg yolk much yellower and chili powder even redder and so forth. So those are now starting to appear on lists of target compounds. Many of them still are not. Here's an interesting one out of China, and that is in May of this year, May 2009, the European Food Safety Authority issued a statement that said they had scientific evidence of finding nicotine in wild dried mushrooms being exported from China. Now, who would ever think, how could you ever get nicotine into mushrooms? You know, nicotine you get in cigarettes, but mushrooms don't smoke cigarettes. I mean, how do you get nicotine into the mushrooms? Well, the answer is that in China, they grow the mushrooms on wood and decaying wood basis. And the problem is insects get into the wood and make it decay. But then the insects eat the mushrooms. So the farmers spray the wood with nicotine, and it kills all the insects. But then what happens to the nicotine? Then it gets into the food chain and becomes part of the mushroom. So now you've got mushrooms containing nicotine. And in fact, it solves one problem, but it creates another. So that's a new non-targeted compound. And then lastly, I think you've heard today enough about illegal foods, especially additives. Many additives going into foods in China as well as other countries. Now these additives are there also to make things look better, smell better, taste better. When you go to the store and the market and you see beautiful red meat, the steaks that are beautiful red, or hamburger that is picture perfect red, well, there's a reason it's so pretty, and that is because it's treated with nitrites. Now the nitrites last for a day or two, but after about 3 days, why, pretty soon the nitrites vaporize, and then the meat looks like brown meat instead of red meat. Well, nitrite's not a particular problem, but other things like sodium cyanide that's used for a sweetener, for example, can be problems, and those are other additives. In my home state of California, we have a list of 85,000 chemicals that are used in commerce. That means many businesses, different businesses, such as healthcare, personal care, agriculture, also in the food industry. And those 85,000 are put on a list of suspect contaminants. Now, without going into all the details, these are all being investigated as non-targeted compounds. In other words, you have a large number of non-targeted compounds. This is not just in California. This is in the world today because we use a lot of industrial chemicals. There are some emerging chemicals, however. Some of these emerging chemicals are things like endocrine disruptor compounds. And endocrine disruptor compounds have been studied here in Korea. They cause major problems with newborn children, major deformities. And those you only have to have at the part per billion or the part per trillion range. So in California, these are also being considered as non-targeted compounds because there's so many different kinds of endocrine disruptor compounds. So that's why they're going to the non-targeted compound list. Now, if you skip over to the page labeled non-targeted screening, there's several ways to do screening. And you've heard today a little bit about ion trap mass spectrometry. The reason that can be used for screening is because you get MS spectra. You get the parent ion and daughter ion spectra, which is a good confirmation tool. And you can identify your unknowns by full scan spectra and also by the MS spectra. Okay? Now, the other way to do that is on the right-hand side. Some laboratories are using time-of-flight mass spectrometers. Some are using QTOF. QTOF is a quadrupole analyzer that's put just in front of a time-of-flight mass spectrometer. And the reason is to filter out the ions of interest so that the time-of-flight mass spectrometer gives you cleaner spectra. In the 20 years I spent with Hewlett-Packard, we spent 20 years working on time-of-flight mass spectrometers, and they are definitely a development in the field of analytical chemistry. but they're no longer the state of the art because there's many problems, such as molecular weight calibration, which is a very big challenge for those mass specs. The other one is if you put a time of flight in any room, any laboratory, and the temperature goes up or goes down in the morning or in the evening or during the day, they're very temperature sensitive, and the temperature change of 2 degrees means you have to recalibrate. So they're useful tools, but they're semi-quantitative. And the other major problem is that today you can get molecular ions measured to 0.001 AMU. 0.001 AMU. That means that they're accurate to and reproducible to 1 millimass unit. Okay, 1 millimass unit. Now, if you had a mixture of 100 pesticides, for example, and you screen them on a time of flight, and you look at mass, any mass in that spectra, then typically what we find is we get about 8 positive identifications, 8 candidates of pesticides, because you only know the molecular weight to the nearest 1 millimass unit. The alternative to doing that is the exactive mass spec. An exactive, as I said this morning, is called that because it gives you exactly the molecular weight of the unknown compound. Now, time of flight will give you to the nearest 1 millimass unit. The exactive will give you to 0.01 millimass units. So there's a factor of 1,000 difference in molecular weight accuracy. Okay. Now, when you have that kind of data, you get, obviously, because you're screening, you get all the data at the end of the run. So you can test for positives or non-targeted compounds. You get the exact mass, and you get quantitation and confirmation. So you get all of those at the same time. And that's why this is a major breakthrough in food technology. If I show you a picture just quickly of this exactive mass spectrometer, it looks like this. Right here you have the API ion source, that's the atmospheric pressure ionization source, standard interface between an HPLC column and a mass spectrometer, that's standard. Then you go through the ion source in this region here. You go through a region of ion focusing optics, which is up here. That is proprietary patented technology. That's what focuses that beam exactly into this mass spectrometer, which is a quadrupole here, and into the collision cell. So far, it looks like a triple quad mass spec, except the products of the collision or the secondary ionization are then brought back into the Orbitrap mass spectrometer. And time does not allow me today to describe Orbitrap mass spectrometers, but they take an elliptical path down through that tube, and they cycle forwards and they cycle backwards, and they wait until their molecular weight is called, and then you go out to the detector. Now, in fact, what's happening is that typically, Guiping talked about this turbo flow automatic sample preparation technique. That's usually coupled to a HPLC, and the HPLC is coupled to the exact mass spectrometer. Well, with turbo flow sample preparation, you now get exceptional cleanup, and you remove the matrices, and many of our customers are taking the turbo flow mass spectrometer, of which you have some in Korea, the turbo flow sample prep, and putting them directly into the mass spectrometer without any liquid chromatograph, because this is the ultimate high specificity detector. As I say, if the molecular weight of my compound of interest, let's just say, is 350 AMU, okay, this will give me the molecular weight to 350.0000001 AMU. Okay? Now you might ask, how does that do that? And the answer is very carefully. Okay? The point is, now you don't have to do calibrations because this is based on accurate mass. So there's several things that are important. For small molecules and large molecules, we have a huge range of molecular weight from 50 to 4,000. much higher than time-of-flight mass spectrometers, and a linear dynamic range of greater than 10,000 to 1, and sensitivities that are in the part per trillion range. So now you're seeing high mass accuracy, trace analysis, and quantitation. So let me show you a little bit about what we mean by mass accuracy. Now, does anybody recognize that picture? Is that a building here in Seoul? Is that a university or a government building, or what do you think that looks like? Anybody know? I know you know. I know you know. No, it's a bridge. It's a bridge. It's one of the most famous bridges in the United States. Oops. And it's the Golden Gate Bridge in San Francisco. I chose this because it's about 20 minutes from my home. Well, with high resolution, there is no doubt that this is a bridge. With a low resolution, it's not clear that it's a bridge or a building or a truck or what have you. So you see the difference. Now, let's look at what we mean by resolution. And resolution in mass spectrometry simply says that this is the mass that you're measuring, and this is the peak width at the half height. So, for example, if I'm measuring a molecular weight, let's say a molecular weight of 1,000, then it means that this has to be accurate to 0.01 millimass units. That's 10 to the minus 5. 10 to the minus 5, or 10 to the, if this is 10 to the minus 5, and that's 10 to the third, then in fact you're talking about a resolution of better than 1 part per million. Okay? Now, so that's the definition, and that's the way we measure that. And that's standard practice in mass spectrometry. Now, to get mass accuracy is dependent on having high resolution first and foremost. And now the accuracy is measured by taking the true molecular weight. Now, you can calculate the true accurate molecular weight of any organic compound. First of all, you can go to the Merck index and look it up, and it'll give you the molecular weight to 6 significant figures. Okay? Secondly, you can calculate this by taking the exact atomic weights of the hydrogen, the carbon, the nitrogen, the oxygen that are in your organic compounds. And you simply add them up, and you'll calculate the true molecular weight. Now, this is the measured molecular weight that you and I measure in the laboratory with this mass spectrometer, and this, of course, then is the true molecular weight again. So if this molecular weight was 300.000000, that's hypothetical, and this was measured to be 299.99999, then you would have a mass accuracy of 1 part per million. Okay? So you say, gee, this must be very, very hard. It's not hard. We